Hello. This is Nicholas, and this is my fourth video on the Fourier series. Last video I derived the Fourier series using the real version for e to the x, and this time I'm going to go complex. So remember just kind of our tools for the complex Fourier series, our f of x, which will be our e to the x in this case. So that's given by sigma n equals negative infinity to infinity of f of x times e to the I n x. And our f of x again is e to the x. And, is given by c sub n. I'm sorry, I don't know why I put f of x. I was thinking the real Fourier series. C sub n times e to the I n x. And so that c sub n, and a couple of videos ago was 1 over 2 pi, integral from negative pi to pi. This is where the f of x comes in, because it's 1 over 2 pi, integral negative pi to pi of f of x e to the negative I n x dx. And so that's kind of like our toolbox that we're going to use. So we need to just find c sub n. So c sub n is 1 over 2 pi times the integral from negative pi to pi of f of x, which is e to the x times e to the negative I n x. So for now, I'll just write it as e to the x times e to the negative I n x dx. And then what I can do is write this as 1 over 2 pi, integral negative pi to pi. And I can write that as e to the x times 1 minus I n dx. Now, what I can do is actually do the integration. So I would get, what would I get? I would get a 1 over 2 pi times, now I need to use the chain rule here and divide by, I would need to divide by the derivative here, so that's when I take d over dx of negative x I n, I get negative I n. So I would get a I n minus 1 right here, because I would have a negative 1 minus I n on the bottom, and that's I n minus 1. Yeah. That's just integration. You could do it out and if you wanted. I kind of did that in my head there. So we would have e to the x times 1 minus I n evaluated from negative pi to pi. And when we do that, so we plug in pi, we get e to the pi times 1 minus I n minus e to the, I'm going to write it as pi times I n minus 1. In other words, distribute the negative sign on the inside, over 2 pi times I n minus 1. And that's our c sub n. So now we can plug that definition of c sub n into the Fourier series, and we're going to get the sum from negative infinity to infinity. And this is all going to be equal to e to the x. So that's going to be e to the pi times 1 minus I n minus e to the pi times I n minus 1 over 2 pi times I n minus 1 times e to the I n x. And that is the complex Fourier series for e to the x. And again, x going from negative pi to pi. So now the thing that I was most curious about is, again, let's let x equal 0 and see what we get. If we let x equal 0, we get 1 equals sigma n equals negative infinity to infinity of, and now notice that e to the I n times 1 So in other words, e to the in times 0, right? Because we're letting x equal 0. That just gives us e to the 0, which is just 1 again. So this just becomes a 1 here. And now we can say that 1 is equal to sigma n equals negative infinity to infinity of e to the pi times 1 minus in minus e to the pi times in minus 1 over 2 pi times in minus 1. And we can fool around with this a little bit more, right? So what we can do is we can write that that's the same thing as sigma n equals negative infinity to infinity of, we can write e to the pi times, right? I can make this e to the pi times e to the negative in. E to the negative in, or e to the negative pi, I would multiply by the pi there, e to the negative in pi. So we would get cosine of pi n minus I times the sine of pi n by Euler's identity. And I know I'm going to run out of room, so I'm going to move this down here already. So that's from that first part there. So the second part, now we get e to the pi. Oh, so what I'm going to basically do with the second part right here, I'm going to make this e to, my laser was still on. I'm going to make it e to the negative pi times e to the pi in. So we get yeah. Okay, so we get e to the negative pi, oops, dang damn it, e to the negative pi times e to the pi in, which is cosine of pi n, plus I times the sine of pi n. And this is all over 2 pi times in minus 1. And all this is equal to 1. So if someone asks you for a really complex form of, pun intended, a complex form of 1, you could give them this. So now the thing I would want to note is that n is integer values, basically, right? It's the set of integers that n is containing. So for every integer n, cosine of pi n is going to give us a 0. So that goes away, and that goes away. That was the whole point of kind of expanding like I did there. And then for every integer n, cosine of pi n gives us a negative 1 to the n, and here as well. So that really simplifies things down, because now we have sigma n equals negative infinity to infinity of e to the pi minus e to the minus pi, times negative 1 to the n over 2 pi times in minus 1 is equal to 1. And now I can take this part here, which is a constant, and bring it out front of the summation, and then divide by it or multiply by the reciprocal. And what I'll get is that 2 pi over e to the pi minus e to the minus pi is equal to sigma n equals negative infinity to infinity of negative 1 to the n over in minus 1. And nicely, I could in fact write this as the following: pi times the hyperbolic cosecant of pi is equal to sigma n equals negative infinity to infinity of negative 1 to the n over in minus 1. That right there is a very strange result, in my opinion. And I guess my question to you is, I don't think I've made a mistake anywhere in the math at all, but how is that possible? X is definitely in the interval of convergence of the Fourier series, right? Because it's on an interval of length 2 pi. And 0 is definitely within the interval negative pi to pi. It's not an endpoint or anything, so it definitely like converges, I guess. but that I in the sum is really bothering me. How can this imaginary or complex sum, right, for all like integer values of n, this like alternating in sign complex sum, converge first of all, and then converge to a real number, right? Pi hyperbolic cosecant of pi. That just seems like it can't be true. Like it's a complex sum. It's got this I in there. I mean, I don't know. Maybe like I don't know. Maybe you rationalize or multiply by the complex conjugate of the infinitely many denominators, and I don't know, something maybe miraculous cancels out or whatever. But so I don't know if you could give me some like insight, or maybe why this happens, or if I did something wrong, or if this is even true, or what it might mean. I would really appreciate it. Anything you could give me here, because I've been thinking about it for a couple days, and I've been like, what does that even what does that even mean? So I really hope you can help me with my question here. And hopefully this, like, going through the complex Fourier series for e to the x also like gives you a feel for why I think at least the complex version is easier, right? Much less algebra and integration and all this stuff. I guess with that